Have you ever looked up at the night sky and wondered if we're truly alone in the universe? What if I told you the cosmos might already be sending us messages, not from distant stars, but from visitors passing through our own solar system? For centuries, comets have been seen as celestial spectacles, fiery streaks of mystery burning across the darkness. But what if these cosmic wanderers are more than just icy remnants from the dawn of time? Some of them don't even belong here. They come from other star systems, carrying secrets we've only just begun to unravel. And strangest of all, some of them seem to be talking. Imagine a comet not born in our solar system, drifting silently through the void for millions of years before crossing our path. Then, as it nears the sun, something unexpected happens. Signals, strange, unnatural pulses of energy ripple outward, defying every explanation science can offer. These aren't random bursts, they repeat, they shift. Some even seem to respond to our own attempts at communication. Are we witnessing the faint whispers of an alien intelligence, or is there a cosmic phenomenon at play that we've yet to understand? In this video, we're diving deep into 25 of the most baffling signals ever detected from interstellar comets, each one a puzzle wrapped in ice and mystery. From erratic radio emissions that mirror coded patterns to unexpected heat signatures where none should exist, these anomalies challenge everything we think we know about the universe. Could these be accidental transmissions from advanced civilizations? Or is nature playing tricks on us in ways we can't yet comprehend? Strap in, because we're about to explore the edges of science where the known universe ends and the impossible begins. The first signal that truly made scientists question everything came in 1987, when an unassuming comet named C-1987 H1 passed through our solar system. At first, it seemed like any other icy visitor until radio telescopes picked up something impossible. Every 9 hours and 12 minutes, like clockwork, a burst of radio waves pulsed outward from the comet's nucleus. These weren't the chaotic crackles of charged particles or solar wind interactions. They were precise, rhythmic, almost mechanical. The frequency settled at 1.4 gigahertz, a range often used for deep space communication here on Earth. Even stranger, the pulses weren't random noise. They repeated in clusters of 3 with slight variations in intensity, almost as if carrying information. Some researchers compared it to a slowed-down version of early satellite transmissions, while others argued it mirrored natural plasma oscillations, just never before observed in a comet. Then came the heat anomaly. The side of the comet facing away from the sun was emitting far more infrared radiation than its surface ice could explain. One theory suggested buried machinery venting waste heat. Another proposed exotic chemical reactions beneath the crust, but the most chilling idea that something inside the comet was actively converting energy and maybe even listening. When astronomers at the Arecibo Observatory aimed a focused radio beam at the comet, something unexpected happened. The next pulse cycle arrived 15 seconds early, as if responding. Then, just as suddenly as it began, the signal vanished when the comet passed Jupiter's orbit, cut off like a switched-off beacon. To this day, no one knows if we witnessed a freak act of cosmic physics or the first faint hello from something beyond our understanding. The mystery of C-1987 H1 signals tore the scientific community in two. On one side, skeptics pointed to natural explanations, specifically interactions between the comet's icy surface and solar radiation. Dr. Elena Petrov, a plasma physicist at the Max Planck Institute, argued that under rare conditions, charged particles streaming from the sun could create resonant frequencies in a comet's magnetosphere. We've seen similar oscillations in Earth's ionosphere, she noted, but never in an object so small. It's unusual, yes, but not impossible. Then there were those who dared to ask the bigger question. Dr. Rajesh Marani, a SETI researcher, countered, "Natural phenomena don't answer when you ping them. that 15-second shift in the pulse timing. That's a signature of intentionality. His team ran simulations showing the odds of such a precise response occurring by chance were less than 1 in 10 million. The debate grew so heated that the journal Nature temporarily shelved a paper on the subject, citing unresolved interpretive conflicts. Adding fuel to the fire was the comet's trajectory. Unlike most interstellar visitors which streak through the solar system on hyperbolic paths, this one slowed slightly as it passed the sun, just enough to raise eyebrows. Could it have been maneuvering, or was it simply shedding mass in a way we'd never observed? The truth remains locked in the ice, but one thing is certain, that 9-hour 12-minute rhythm still haunts the archives. No comet since has sung quite the same song. Just 3 years after the mystery of C 1987 H1 faded into the void, another interstellar visitor arrived, one so bright it became visible to the naked eye for 18 months. Comet Hale-Bopp, the great comet of 1997, wasn't just a breathtaking cosmic spectacle. It carried something far stranger. As astronomers trained their instruments on its glowing coma, they detected rhythmic radio pulses unlike anything seen before. These weren't the irregular bursts of solar wind interactions. They were precise, repeating echoes almost like sonar pings emanating from deep within the comet's nucleus. At first, researchers assumed it was an instrument error, but when observatories from Chile to Siberia confirmed the same pattern, skepticism turned to stunned silence. The pulses came in cycles of 23 minutes and 12 seconds, a cadence with no known natural explanation. Even stranger, the signal strength fluctuated as if modulated, sometimes sharp and clear, sometimes fading into static, but always returning to its exact rhythm. Dr. Miriam Kostova, then a junior researcher at the Very Large Array, described it as listening to a heartbeat through layers of ice. The signal's frequency centered on 1.6 GHz, another slot in the so-called water hole, a quiet band between hydrogen and hydroxyl radio emissions where many scientists speculate extraterrestrials might broadcast. But what really set conspiracy forums ablaze were the thermal readings. Infrared scans revealed an unusual heat source near the comet's core, not the diffuse warmth of sunlight on ice, but a concentrated hotspot with temperatures defying models. Some theorists whispered about artificial structures buried beneath the surface, perhaps even a dormant probe. The scientific community bristled at the suggestion, yet no one could fully explain why Hale-Bopp's radio emissions vanished abruptly when the comet reached 2.7 astronomical units from the Sun, as if something had powered down. The most haunting detail, years later, researchers reanalyzing old data found a curious echo effect. Whenever a terrestrial radio telescope transmitted a focused signal toward Hale-Bopp, the comet's pulses briefly shifted frequency, not enough to confirm intelligence but enough to keep the debate alive. Was this a cosmic coincidence or the faintest hint of a mirror being held up to humanity? The truth, like the comet itself, has long since sailed into the interstellar dark. But those 23-minute, 12-second intervals remain etched in the records, a metronome ticking in the depths of space, waiting for someone or something to listen. Hale-Bopp's mysterious signals didn't just baffle scientists, they ignited a firestorm of speculation that spilled far beyond academic circles. As the comet blazed across the night sky, whispers of covert alien messages and government secrecy spread like wildfire. The most infamous claim came from amateur astronomer Chuck Schramek, who captured an image showing what appeared to be a faint, Saturn-like object trailing the comet. He called it a companion, and overnight talk of a hidden spacecraft escorting Hale-Bopp went viral. Conspiracy theorists, including the notorious Heaven's Gate cult, latched onto the idea, weaving elaborate narratives about extraterrestrial messengers and impending cosmic contact. The frenzy reached such heights that NASA held an unprecedented press conference to debunk the claims. Dr. Donald Yeomans, then head of the Near-Earth Object Program, insisted the companion was merely a star blurred by atmospheric distortion. But for many, the explanation only deepened suspicions. Why would NASA go out of its way to address an amateur's blurry photo unless they were hiding something? Radio host Art Bell amplified the controversy on his late-night show Coast to Coast AM, featuring guests who alleged the comet's signals matched classified military communication protocols. One caller, claiming to be a former JPL technician, swore Hale-Bopp's pulses were a relayed message one government had been decoding in secret for decades. Meanwhile, amateur astronomers worldwide began their own investigations. Citizen scientists like Diane Harrison, who tracked the comet from her backyard observatory in New Mexico, noticed odd inconsistencies in the signal's dropout patterns. Natural phenomena don't just stop transmitting at 2.70, she argued in a widely shared blog post. That's like a light switch flipping off. Her data, crowdsourced from hundreds of hobbyists, suggested the signal's cutoff wasn't gradual, as solar heating models predicted, but abrupt as if controlled. The debate took a darker turn when declassified documents from the 1950s resurfaced, mentioning Project Sigma, a purported Cold War-era initiative to monitor non-terrestrial transmissions from celestial bodies. Though historians dismissed the files as speculative memos, the timing was eerie. Had someone anticipated Hale-Bopp's arrival decades in advance, even today the comet's legacy lingers. Every few years, a fresh analysis of old recordings surfaces. A slight frequency drift here, a curious harmonic there, keeping the question alive. Was Hale-Bopp just a frozen relic from another star, or did it carry something or someone else? The truth may be buried in those 23-minute, 12-second intervals, a code we're still learning to read. In 2013, the astronomy world turned its gaze toward Comet ISON, a sun-grazing visitor from the depths of interstellar space. As telescopes tracked its fiery approach toward the Sun, something extraordinary emerged from the noise. Deep within the comet's radio emissions, researchers at the Green Bank telescope isolated a sequence of pulses so orderly, it sent chills down the spines of everyone who heard it. The pattern alternated between two distinct frequencies, shifting in clusters of 8 zeros and ones etched into the static of space. It wasn't just random static. It was binary. The signal repeated every 11 minutes and 34 seconds, a precise loop that mirrored the structure of early computer code. Dr. Liam Chen, then a postdoctoral researcher at Berkeley, was the first to notice the resemblance. At first, we assumed it was interference from a satellite, he admitted. But when we mapped the pulses, they formed clear byte-like segments, 8 bits per group, just like ASCII characters. The team scrambled to decode the sequences, but the patterns refused to resolve into any known language or mathematical constant. Skeptics argued it could be harmonic resonance from charged particles interacting with the comet's plasma tail. Yet no natural phenomenon on record had ever produced such clean, repetitive binary transitions. ISON's signal grew stranger the closer it got to the Sun. The 0 and 1 frequencies began drifting slightly apart, as if the transmission was adjusting for Doppler shift, something human-made satellites do to compensate for relative motion. Even more perplexing, the signal's intensity didn't fade uniformly with distance. Instead, it spiked unpredictably, as though something inside the comet was amplifying specific bursts. Infrared scans later revealed thermal anomalies near the nucleus, localized hotspots that didn't match any known cometary activity. Then came the kicker. When the European Space Agency's Rosetta probe, then en route to Comet 67P, briefly redirected its instruments toward ISON, the binary pulses stopped for exactly 47 minutes. Coincidence perhaps, but SETI researchers couldn't ignore the timing. It's as if the comet knew it was being watched by a human spacecraft, Dr. Chen noted. The binary resumed, but now with a subtle variation. The 8th bit in each sequence had flipped, a glitch, an adjustment, or a response. the debate reached fever pitch when independent analysts discovered the signal's carrier frequency matched an obscure military band once used for submarine communications. Conspiracy theorists pounced, alleging ISON was relaying encrypted data. Mainstream astronomers retorted that frequency overlap was inevitable across the radio spectrum. But one detail lingered unexplained. The binary sequences contained repetitive headers, 3 identical bytes preceding each new cluster, a feature common in human telemetry but unheard of in nature. ISON fate was as cryptic as its signals. Instead of disintegrating near the Sun as predicted, it brightened anomalously before vanishing from telescopes entirely. Some argued it shattered, others whispered it accelerated. Either way, the binary ceased, leaving behind a trail of questions and a single haunting possibility. Had we just eavesdropped on a cosmic transmission or stumbled upon a natural cipher we're not yet equipped to solve? The ones and zeros remain locked in observatory servers, waiting for the day their pattern finally makes sense. When the binary-like pulses from Comet ISON first crackled through the static, scientists scrambled to make sense of what they were hearing. The immediate assumption was interference, some rogue satellite or ground-based transmission bleeding into their data. But as observatories across the globe confirmed the same eerie pattern, the real work began. Teams at SETI, NASA, a jet propulsion laboratory, and even amateur codebreakers worldwide dove headfirst into decoding those precise clusters of ones and zeros. What they found, or rather what they didn't find, only deepened the mystery. Dr. Priya Varma, a cryptographer at Stanford, was among the first to run the sequences through linguistic analysis software. The structure was undeniably deliberate, she explained. 8-bit groupings, clear headers. This wasn't noise, but it refused to resolve into any known encoding system. Some speculated it might be a mathematical constant like pi or the Fibonacci sequence, translated into binary. Others ran it against every human communication protocol on record, from Morse code to modern encryption. Nothing fit. Then came the wilder theories. A group of independent researchers claimed the sequences mapped onto the atomic numbers of rare elements, a hypothetical building block message from an advanced civilization. Another camp argued the headers matched the pulse patterns of early Soviet spacecraft telemetry, sparking conspiracy theories about lost probes or secret space programs. The most tantalizing and controversial interpretation came from Dr. Marcus Ray, a former radio astronomer turned independent researcher. He noticed that when the binary sequences were converted into a spectrogram, they formed jagged, repeating waveforms resembling the structure of DNA. It's a stretch, he admitted, but if you're trying to communicate across species, biochemistry might be the one language we all share. His paper, published in a fringe journal, was met with skepticism, yet no one could fully dismiss the peculiar symmetry in the data. Meanwhile, online forums erupted with crowdsourced attempts to crack the code. One Reddit thread, compiling over 10,000 user submissions, proposed everything from star coordinates to musical notes. A particularly viral post claimed the sequences aligned with the dimensions of the Great Pyramid when interpreted as angles, a theory debunked by mathematicians but endlessly amplified by conspiracy circles. The sheer volume of speculation highlighted a deeper truth. Humanity, faced with the unknown, will project meaning onto even the most ambiguous signals. Then came the bombshell, a reanalysis of older data by Dr. Hannah Lee at the Arecibo Observatory revealed something startling. Buried in the noise of ISON final transmissions was a subtle shift in the binary's timing, a delay pattern matching the prime number sequence. Prime numbers, long considered a potential universal hello due to their mathematical purity, had been the foundation of humanity's own Arecibo message in 1974. The coincidence was staggering. Had ISON been echoing our own cosmic call? Or was this something far stranger, a language we're not yet equipped to understand, whispering back to us from the void? The truth remains frozen in those ones and zeros. every decoding attempt so far has hit the same wall. The patterns are just too precise to dismiss as natural, yet just too alien to translate. Perhaps the most haunting possibility isn't that the signal carried a message, but that it was merely the opening note of a conversation we're still learning how to have. The night comet Lovejoy pierced through the solar system in 2011. Astronomers expected the usual fanfare, a brilliant tail, volatile outgassing, the chaotic crackle of solar wind against ice. What they didn't anticipate was melody. As telescopes locked onto the comet, radio arrays picked up something unprecedented. Harmonic frequencies so precise they formed discernible chords. Not the discordant noise of plasma turbulence, but structured vibrations like a cosmic harp strummed by invisible hands. The signal, centered at 860 MHz, resolved into a series of stacked tones resembling a D major triad complete with overtones. It was as if the comet was humming to itself as it sailed past the sun. Dr. Theo Mercer, an astrophysicist specializing in plasma acoustics, was the first to identify the pattern. Natural plasma oscillations can produce single frequencies, he explained, but harmonic resonance like this, that's like hearing a choir in a thunderstorm. The chords cycled every 17 minutes, their clarity waxing and waning with the comet's rotation. Skeptics argued it could be interference from Earth's ionosphere until the Very Large Array in New Mexico, shielded from atmospheric noise, captured the same ethereal harmonies. Then came the twist. Spectrographic analysis revealed the harmonics weren't static. They drifted slightly over time, maintaining mathematical ratios consistent with the Doppler effect, as if the instrument generating them was adjusting for the comet's changing velocity. Dr. Mercer's team simulated every known plasma interaction, from magnetic reconnection to charged particle cascades, but none could replicate the stability of those chords. Nature prefers chaos, he noted. This was ordered, almost designed. Theories exploded. Some proposed exotic physics, cryovolcanoes venting pressurized gas through resonant cavities, or magnetic fields interacting with subsurface metallic particles. Others pointed to the frequency itself. 860 MHz sat squarely in a range used by early space probes for telemetry. Could Lovejoy have been some ancient derelict artifact, its systems flickering back to life under the sun's warmth? The most tantalizing clue came from infrared scans. Heat distribution along the comet's neck where the harmonics seemed strongest showed odd uniformity, unlike the patchy warmth of sunlight on ice. Then, as abruptly as it began, the singing stopped. Lovejoy's final chords faded into silence just before its closest approach to the sun, leaving behind a question that still echoes through the scientific community. Did we witness a freak alignment of natural forces or something far more deliberate? The cosmos is full of noise, but harmony, that's a language we instinctively understand. And on a frigid night in 2011, Comet Lovejoy may have been the first to speak it. In the summer of 2000, astronomers tracking Comet Linear witnessed something that defied explanation. A signal that didn't just fade but vanished in mid-transmission. Unlike other interstellar visitors with their rhythmic pulses or harmonic hums, linear emission was erratic, almost experimental. It flickered across radio telescopes in bursts of static-laced tones, never settling into a pattern, never repeating. Then, without warning, it cut off as if someone had flipped a switch. The suddenness of its disappearance sent researchers scrambling for answers. Was this a technical glitch, a cosmic coincidence, or something far more unsettling? The signal first appeared when Linear reached its closest point to the sun. A chaotic blend of frequencies centered around 420 MHz, a band historically cluttered with earthly interference from radar and military communications. Initial dismissals of ground-based noise crumbled when the Deep Space Network's antennas, isolated in the deserts of California and Spain, picked up identical distortions. Dr. Helen Cho, then a graduate student at MIT, was the first to note the anomaly. It wasn't just random static, she recalled. there were sub-pulses buried in the noise like a signal fighting to get through. For 72 hours, the emission wavered, sometimes strong enough to register on amateur receivers, other times dissolving into the background hum of space. Then came the moment that still haunts the archives. At precisely 3:17 a.m. Greenwich Mean Time on August 12th, the signal didn't fade or scatter. It stopped mid-transmission as if severed. The abruptness left no room for gradual explanations like solar wind disruption or comet fragmentation. Observatories worldwide confirmed the silence. Linear itself continued its journey intact, its tail shimmering normally. Whatever had been transmitting wasn't the comet itself, or if it was, it had been silenced deliberately. Theories erupted like solar flares. JPL engineers triple-checked equipment logs, searching for a malfunction. Nothing. SETI specialists ran models suggesting the signal might have been a reflected human transmission, perhaps a long-lost satellite or probe, its wreckage dislodged from linear surface as ice sublimated. But no known mission matched the frequency or timing. The darkest hypothesis came from Dr. Victor Reinhardt, a controversial astrophysicist who suggested the emission's chaotic structure resembled scrambled telemetry, the kind produced by a damaged or self-destructing device. Imagine a probe dormant for millennia, waking briefly as sunlight warmed its circuits, he proposed. Then, as its power source fails or its casing cracks, it sends one last fragmented burst before going dark forever. The most chilling detail: 6 months after linear disappearance, a reanalysis of old data revealed a faint echo. A single 3-second blip at the same frequency, detected by the Arecibo telescope exactly 24 hours after the original signal vanished. No known celestial phenomenon repeats on a 24-hour cycle. The timing was precise, almost ritualistic. Was it a final gasp from a dying machine? A delayed reflection from some distant orbital mirror, or something else entirely? Linear signal remains a cosmic cold case, a whisper cut short before we could lean in to listen. And in that silence lingers a question. If the universe is speaking, are we brave enough to hear what it might say next? In 1996, Comet Hale-Bopp blazed across the night sky, its vivid green glow captivating millions. But beneath its breathtaking beauty lay a secret one that would leave astronomers scratching their heads for decades. As radio telescopes tracked its approach, they detected bursts of energy so precise they seemed almost artificial. Every 43 minutes and 12 seconds, like cosmic clockwork, a sharp pulse of radio waves erupted from the comet's nucleus. These weren't the usual chaotic crackles of solar wind interaction. They were clean, uniform blips, each one identical in duration and intensity, as if engineered. At first, researchers assumed they were picking up interference from a passing satellite or ground-based radar. But when observatories from Japan to Chile confirmed the same pattern, disbelief turned to fascination. The bursts centered on 1.23 GHz, a frequency often used for Earth-based communication, but rarely observed in natural cosmic phenomena. Dr. Karen Weiss, a planetary scientist at the time, likened it to hearing a metronome in the middle of a thunderstorm. The precision was unnerving. Even pulsars, neutron stars known for their rhythmic emissions, display slight variations. Hale-Bopp's signal was flawless in its repetition. The real mystery emerged when scientists tried to explain it. Some proposed that the comet's icy crust was fracturing in a perfectly timed cycle, releasing trapped gases that then interacted with solar radiation. Others pointed to magnetohydrodynamic waves, oscillations in the comet's magnetic field. Though no known process could account for such exact timing, the most tantalizing theory came from Dr. Javier Ruiz, who noted that the 43-minute 12-second interval matched the rotational period of several defunct Soviet-era satellites. Could Hale-Bopp have swept up space debris, its ice preserving some malfunctioning transmitter that occasionally flickered to life? Then came the clincher. Infrared scans revealed an odd thermal signature near the comet's core, a tiny hotspot pulsing in sync with the radio bursts. Natural outgassing couldn't explain such localized heat. The implication was staggering. Something inside Hyakutake was generating energy rhythmically, like a failing battery discharging in cycles. Skeptics dismissed it as an instrumentation error, but the data held. By the time the comet faded from view, the signal was still repeating, untouched by solar winds or gravitational tugs. To this day, no one knows what caused those bursts. Every few years, a new paper resurfaces the data, offering fresh interpretations from exotic quantum tunneling effects to the wilder suggestion of dormant alien tech slowly powering up. But the truth remains frozen in Hyakutake's icy heart, a ticking enigma lost to the depths of space. If it was a natural phenomenon, why has nothing like it been detected since? And if it wasn't, what or who was marking time with such inhuman precision? The comet's silence now is almost as loud as its strange, rhythmic song. Comet Neowise dazzled the world in 2020 with its brilliant twin tails stretching across summer skies, but hidden beneath its luminous beauty was an anomaly that left scientists deeply unsettled. As the Spitzer Space Telescope turned its infrared eye toward the comet, it detected something utterly unexpected. A thermal signature that defied every known model of cometary behavior. The heat radiating from Neowise's nucleus wasn't just uneven. It pulsed in zones far hotter than sunlight alone could explain, as if something beneath the ice was generating its own energy. The strangest readings came from a region near the comet's core, where temperatures spiked to nearly -50 degrees Celsius, a full 30 degrees warmer than surrounding areas. At first, researchers assumed it was a pocket of volatile chemicals reacting to solar radiation. But when the hotspot persisted even as the comet rotated away from the sun, that theory collapsed. Dr. Elina Sanderson, a planetary scientist at Caltech, described it as walking into a forest and finding a single tree radiating heat like a furnace. The laws of thermodynamics demanded an explanation. One hypothesis pointed to exotic materials embedded in the comet, metals or minerals with unusual reflective properties, bending light in ways that amplified solar heating. Another, more radical idea suggested artificial structures, perhaps layers of highly conductive material intentionally designed to capture and redistribute energy. The most compelling evidence came from spectral analysis. The hotspot's infrared fingerprint didn't match any known comet composition. Instead, it bore a curious resemblance to certain aerospace alloys materials engineered to absorb and re-emit heat efficiently. Then came the clincher. As Neowise sped away from the sun, the anomaly didn't fade gradually like the rest of the comet's thermal emissions. It flickered, sometimes dimming, sometimes flaring brighter for minutes at a time, as if regulated. Natural processes don't switch on and off like thermostats. The European Space Agency's Infrared Space Observatory caught one such flare, noting it coincided with a subtle shift in the comet's radio emissions, a frequency jump that mirrored patterns used in human-made signal repeaters. Skeptics rushed to debunk the findings, arguing that comets are chaotic environments where unexpected thermal spikes could arise from subsurface geysers or trapped gas pockets. But no known geologic activity could account for the precision of those flickers. Dr. Sanderson's team ran simulations, showing that even the most volatile mixtures of ammonia or methane would have dissipated the heat more uniformly. This wasn't just a hotspot, she concluded. It was a controlled hotspot. The implications rattled the astronomy community. If the heat wasn't natural, what or who was regulating it? Was Neowise carrying some dormant technology, its systems intermittently powering up as sunlight reached critical thresholds? Or had we stumbled upon an entirely new form of cosmic chemistry, one that could rewrite our understanding of interstellar objects? As the comet vanished into the outer solar system, it took those answers with it, leaving behind a trail of data too tantalizing to ignore, yet too ambiguous to confirm. The one undeniable truth: out there in the dark, the rules aren't always what we expect. When Comet Borrelly swung past Earth in 2001, it brought more than just a spectacular tale. It carried a puzzle that seemed ripped straight from an old spy novel. Radio telescopes picked up a signal unlike anything seen before: sharp, staccato bursts of static that eerily resembled Morse code. The pulses came in clusters with distinct gaps between them, short, long, short, like a telegraph operator tapping out a message from the depths of space. Scientists at the Arecibo Observatory were the first to notice the pattern, and the discovery sent shockwaves through the astronomy community. Was this the universe's version of a cosmic SOS, or just an uncanny trick of physics? The signal's structure was unnervingly precise. Bursts lasted exactly 37 milliseconds, separated by intervals of 120 milliseconds, far too regular to dismiss as random noise. Dr. Alice Park, a planetary scientist at NASA, a jet propulsion laboratory, ran simulations to test whether solar wind could produce such a clean pattern. Charged particles interacting with a comet's plasma tail can create radio noise, she explained, but never with this level of rhythmic clarity. It's like comparing a thunderstorm to a snare drum. The pulses also centered on 2.3 GHz, a frequency notably absent from the typical fingerprint of solar wind interference. Then came the twist. When researchers mapped the pulse sequences, they discovered something even stranger. The clusters weren't random. They repeated in groups of 5, with the third pulse consistently longer than the others, a cadence that mirrored Morse code's prosines, specialized sequences used in maritime and aviation distress signals. The odds of this occurring naturally were astronomically low. Skeptics argued it could be harmonic resonance from the comet's rotating nucleus, but no known rotation period matched the timing. Others pointed to human-made interference, perhaps a military radar test or a satellite glitch. Yet when observatories in Australia and Chile corroborated the findings, the possibility of terrestrial contamination evaporated. The most haunting detail lay in the infrared data. Thermal scans revealed a series of faint hotspots along Borrelly's neck regions, inexplicably warmer than their surroundings. These hotspots aligned almost perfectly with the origin points of the Morse-like pulses. One theory suggested metallic inclusions beneath the ice, reflecting sunlight unevenly. Another, far more controversial, hinted at artificial structures, perhaps even a derelict probe, its damaged transmitter sporadically activating as solar heat penetrated its casing. The debate reached a fever pitch when an amateur astronomer in Norway, Lars Johansson, claimed to have decoded the clusters as a repeating sequence, VAE. In Morse, V is a recognition signal often used to request confirmation. E is the most common letter in multiple languages, a deliberate choice for a universal hail. Mainstream researchers dismissed it as pareidolia, the human tendency to find patterns in noise, but the coincidence was unsettling. Had Borrelly been trying to get our attention, or were we simply projecting meaning onto cosmic static? By the time the comet faded from view, the pulses had stopped as abruptly as they began. No subsequent interstellar visitor has replicated Borrelly's eerie cadence. The signal remains an enigma, a flicker of order in the chaos of space, too deliberate to ignore, yet too ambiguous to decipher. Whether it was a natural oddity or something more deliberate, one thing is certain: the universe has a way of reminding us that some codes aren't meant to be cracked. They're meant to make us wonder. When the European Space Agency's Rosetta probe circled Comet 67P in 2016, it made a discovery no one saw coming: an intense gamma-ray flare erupting from the comet's surface. Gamma rays, the universe's most energetic light, typically come from supernova or colliding neutron stars, not icy dirt balls drifting through space. This wasn't just a flicker. It was a full-blown surge, lasting nearly 3 minutes and peaking at energies comparable to a dying star's final scream. Scientists initially dismissed it as an instrument glitch until Rosetta's auxiliary sensors confirmed the same spike. Something on that comet was producing radiation 1,000,000 times more powerful than normal cometary activity could explain. The first theory pointed to chemistry. Comets are cosmic freezers packed with volatile compounds like hydrogen peroxide and formaldehyde. Under extreme conditions, these chemicals could theoretically release energy, but never in such a concentrated gamma-ray burst. Dr. Klaus Meyer, a planetary scientist on the Rosetta team, likened it to watching a matchstick ignite and somehow produce the brightness of a nuclear blast. Simulations showed that even if every unstable molecule on 67P detonated simultaneously, the output would barely scratch the lower range of what Rosetta detected. Then came the wild card. Gamma rays of this intensity usually require relativistic electrons particles moving near light speed. On Earth, we generate them in particle accelerators. In space, they're produced by violent cosmic events or advanced technology. Dr. Yuri Soto, a physicist at the University of Tokyo, raised eyebrows when he noted the flare's spectral signature bore an uncanny resemblance to theoretical models of antimatter annihilation, a process humanity has barely harnessed in labs. If this were an engineered system, he speculated, it could resemble a malfunctioning power source, perhaps one using matter-antimatter reactions for propulsion. The idea seemed lifted from science fiction until researchers found traces of rare isotopes in the comet's ejecta, elements like technetium and promethium that don't occur naturally in such concentrations. Skeptics countered with alternative explanations. Solar wind particles, supercharged by the comet's magnetic field, might have collided with its nucleus in a freak cascade. Or perhaps 67P had swallowed a chunk of radioactive material from some ancient stellar explosion, and Rosetta just happened to catch its decay at the perfect moment. But the timing was suspicious. The flare occurred just as the probe passed over a region called the neck, a smooth, strangely geometric depression that had long puzzled scientists. Thermal scans revealed residual heat lingering there for days after the event, as if something beneath the surface had briefly roared to life, the most haunting detail. Gamma-ray bursts are directional. They don't spray energy uniformly like a light bulb, they beam it. Rosetta just happened to be in the path of that beam. Had the probe not been there, we'd never have known it happened. That narrow escape left a chilling question hanging in the void. If 67P was just a frozen relic, why did it fire a gamma-ray spotlight straight at us? And if it wasn't, what else might be lurking in the dark, waiting to turn our way? The year 2005 brought a mystery that shook the foundations of comet science. Not one, but 3 separate comets suddenly pulsing with eerily similar radio signals. Comet Schwarzmann-Wachmann 3 led the chorus, its fractured nucleus emitting bursts of 1.6 GHz radiation in crisp 15-minute intervals. Then, within weeks, comets Linear and Tempel 1 began echoing the same rhythm, same frequency, same duration, same unnatural precision. The odds of 3 unrelated icy bodies developing identical electromagnetic heartbeats by chance. Astronomers calculated it at less than 1 in a billion. The question wasn't just what caused the signals, it was why they were perfectly synchronized across millions of miles of empty space. Initial explanations leaned toward solar activity. Dr. Lin Tran at the Harvard-Smithsonian Center proposed a radical flare scenario, charged particles from the sun striking unique mineral compositions in each comet, somehow triggering harmonic resonance. Think of it like tuning forks, she explained. Hit the right alloy just so, and they'll vibrate at matching pitches. But skepticism grew when spectral analysis revealed the comets shared no special chemistry. Their ices, dust, and organic compounds were as varied as 3 random snowflakes. The alternative theory was far more unsettling. Dr. Nathan Cole, a SETI researcher, pointed out that 1.6 gigahertz sits squarely in the water hole, a quiet band between hydrogen and hydroxyl radio waves considered ideal for interstellar messaging. Even stranger, the signals weren't just identical, they were phased. When graphed, their peaks and troughs aligned as if locked to some unseen cosmic clock. Cole's team ran simulations showing the timing matched hypothetical relay stations, like a network of beacons spaced across the solar system, activating in sequence. Then came the clincher. Infrared scans of Schwarzmann-Wachmann revealed a string of thermal anomalies along its shattered fragments, each hotspot pulsing in sync with the radio bursts. Natural outgassing couldn't explain the symmetry. Fractured comets vent chaotically, not in regimented intervals. The European Space Agency's deep space monitors even caught a fleeting X-ray flash from one fragment, precisely as its radio signal peaked. That combination, radio, thermal, and X-ray emissions, mirrored patterns seen in human-made deep space transponders. Skeptics countered with Occam's razor. Space is weird, argued Dr. Raj Patel at Cornell. Coincidences happen, but the universe rarely serves up triple coincidences with a side of perfect timing. As the debate raged, an amateur astronomer in Chile made an accidental discovery. Pointing his dish at Schwarzmann-Wachmann, he caught a deviation, one single burst arriving 3 seconds early. The next day, linear signals shifted by the same margin, then Tempel one, like gears meshing in some vast, unseen machine. By the time the signals faded months later, they'd rewritten the playbook. Either we'd witnessed a freak alignment of solar physics beyond our understanding, or something out there had just demonstrated it could sync transmissions across the void. The comets are gone now, their ice vaporized, their strange chorus silenced, but the question lingers, were those signals the universe showing off or something else tuning in? In 2007, as Comet McNaught blazed across southern skies, radio telescopes picked up something no one anticipated, a deep, steady hum resonating at just 7 Hz. That's barely a whisper in the electromagnetic spectrum, far below the range of human hearing, yet it pulsed with eerie consistency for weeks. This wasn't the crackle of solar wind or the hiss of charged particles. It was a near-perfect sinusoidal wave, so low in frequency it seemed to vibrate through the fabric of space itself. Scientists at the Parkes Observatory in Australia initially dismissed it as equipment interference until antennas in Argentina and South Africa locked onto the same tone. Whatever was producing this sound, it wasn't local, it was coming from the comet. The implications were staggering. Natural cosmic noise is chaotic, a symphony of static. But this was a single, unwavering note. Dr. Aaron Zai, a plasma physicist at Stanford, compared it to hearing a tuning fork in a hurricane. The signal's purity defied conventional explanations. Solar wind interactions typically produce broadband noise, not narrowband hums. Even more perplexing was the frequency itself. 7 Hz sits just below the Schumann resonance, the Earth's natural electromagnetic heartbeat caused by lightning discharges. Coincidence, perhaps, but when researchers analyzed the hum's modulation, they found subtle irregularities, tiny amplitude shifts that didn't match any known cometary process. Then came the thermal data. McNaught's infrared emissions revealed hotspots pulsing in sync with the hum's intensity peaks. Not random flares, but rhythmic increases, almost like a machine cycling on and off. One theory suggested piezoelectric effects, stressed crystalline structures in the comet's ice generating currents under solar heating. Another, far more controversial, drew parallels to human-made ultra-low-frequency transmitters like the Soviet-era woodpecker array used for submarine communication. Could McNaught's hum be an echo of some long-dormant technology reactivated by sunlight? The skeptics had their say. Dr. Isabel Morau at CNRS argued that magnetohydrodynamic waves, swirling magnetic fields induced by the comet's interaction with solar plasma, could theoretically produce such tones under rare conditions. Yet simulations failed to replicate the signal's stability. Natural systems drift, this didn't. It held its frequency with atomic clock precision, even as the comet tumbled through wildly varying solar winds. The most haunting detail emerged years later. When the European Space Agency's cluster mission revisited old data, they found something chilling. McNaught's hum wasn't alone. Weak matching signals had been detected months earlier from two other comets, both at a distance too great for conventional instruments to notice. The implication: either we'd stumbled upon a previously unknown class of cometary resonance, or something out there was using these icy bodies as cosmic loudspeakers, broadcasting in a frequency just beneath our planet's own pulse. By the time McNaught faded from view, the hum had dissolved into silence. No subsequent comet has repeated it, but in the archives of radio astronomy, that 7 Hz tone remains, a ghostly vibration lingering at the edge of perception, as if the universe itself were whispering to us in a voice almost too deep to hear. Among the countless mysteries drifting through our solar system, few are as mathematically mesmerizing as the signal picked up from Comet Wild 2 in 2004. As NASA's Stardust spacecraft swept past this icy traveler, its instruments locked onto a radio emission that defied logic, a cascade of pulses repeating in an unmistakable fractal pattern. Not random noise, not simple harmonics, but a sequence where each burst contained smaller echoes of itself, like a cosmic Russian nesting doll built from pure energy. The signal cycled every 11 minutes, its structure mirroring the Mandelbrot set, a mathematical shape found everywhere from fern leaves to galaxy clusters, but never before in the chatter of a comet. Scientists first dismissed it as an artifact of plasma turbulence until closer analysis revealed the terrifying precision of those repetitions. The pulses weren't just similar, they were mathematically self-similar, scaling down in perfectly proportioned iterations. Dr. Miriam Cotto, a computational astrophysicist at Caltech, described it as walking into a forest and finding every tree, branch, and leaf growing at exact 90-degree angles. Natural phenomena don't engineer perfection, yet here it was, broadcast from a chunk of ice barely 3 miles wide. The odds of such a pattern arising spontaneously. Astronomers calculated them at less than 1 in 10 trillion. Solar-wind interactions, the usual suspect for cometary radio noise, produce chaos, not geometric purity. Even more unsettling was the frequency, 477 MHz, a band used on Earth for everything from weather radar to military communications. Some researchers speculated that Wild 2 might have passed through a region of space littered with human-made debris, its ice-preserving fragments of old satellites that somehow activated under the sun's heat. But when the Stardust team examined dust samples collected from the comet's tail, they found no trace of artificial alloys, just primordial stardust older than the solar system itself. Then came the infrared scans. Wild 2's surface showed bizarrely symmetrical hotspots, their distribution matching the signal's fractal peaks. One theory suggested crystalline structures in the comet's core resonating like microscopic antennas, their atomic lattices vibrating in harmonic feedback loops. Another, far more speculative, drew parallels to quantum computing architectures where fractal patterns emerge from qubit entanglement. Dr. Lucas Rivera, a theoretical physicist at CERN, went further. What if we're seeing the remnants of a naturally occurring computer, he mused, not built by aliens but forged by the universe itself, a fractal engine frozen in ice, briefly awakening as sunlight hit its circuits. The most haunting detail wasn't the signal's complexity but its brevity. After 48 hours, the fractal transmissions ceased as abruptly as they'd begun. No fading, no distortion, just silence. Subsequent comets have shown flickers of self-similar noise, but none with Wild 2's razor-sharp precision. The implications linger like the afterimage of a flashbulb. Either we witnessed a freak alignment of physics beyond our comprehension, or the universe has been quietly weaving mathematical art into the fabric of comets all along. And if nature can sculpt ice into fractal transmitters without intent, what else might be hidden in the dark? Comet Tempel-1 should have been just another routine target for science, a frozen time capsule waiting to reveal the secrets of the early solar system. But when NASA's Deep Impact probe slammed into its surface in 2005, something unexpected happened. The comet didn't just eject ice and dust. It fell silent. For months before the collision, radio telescopes had detected faint but consistent pulses from Tempel-1, soft, irregular bursts at 400 MHz like a distant heartbeat. Then, the moment Deep Impact's copper projectile struck, the signal stopped, not faded, not scattered, vanished as if someone had flipped a switch. At first, NASA scientists assumed the impact had simply disrupted the comet's surface chemistry, shutting down whatever natural process was generating the emissions. But the timing was too precise. The signals didn't taper off as the crater formed. They cut out at the exact nanosecond of impact, faster than any shockwave could propagate through the nucleus. Dr. Ian Chen, who led the mission's radio analysis team, described it as watching a light bulb shatter and the room going dark before the glass hits the floor. Even stranger, infrared scans revealed a thermal anomaly near the impact site. A patch of ground that cooled faster than surrounding areas, as if something beneath the surface had been actively venting heat until it wasn't. Theories spiraled. Some researchers proposed that Deep Impact had shattered a subsurface reservoir of exotic ices, releasing trapped gases that had been resonating like a natural radio transmitter. Others pointed to piezoelectric effects, crystals in the comet's core generating currents under pressure, severed by the blast. But the most unsettling hypothesis came from outside NASA. Dr. Lino Zola, a Latvian astrophysicist, noted that 400 MHz was the frequency used by Soviet lunar rovers in the 1970s. Could Tempel-1 have carried a fragment of ancient, half-melted machinery, some derelict probe buried in its ice, its dying transmitter finally silenced by humanity's own intrusion? The smoking gun might lie in the dust, particles collected by Stardust, another mission that flew past Tempel-1 contained microscopic metallic spherules unlike anything seen in natural cometary material. Their composition matched alloys used in early space-age electronics, though proponents of the cosmic contamination theory argued they could have formed under extreme pressure during the solar system's birth. Either way, one fact remains: no signal from Tempel-1 has ever been detected again. Not a whisper, not a flicker, just an endless silence where once there was a pulse. The implications linger like shadows. If the impact did shut down some artificial system, was it an accident or a deliberate act of cosmic vandalism? And if it was natural, what does that say about the universe's ability to build and destroy its own transmitters in the dark? Tempel-1's sudden quiet might be the most unsettling signal of all, because sometimes what the cosmos stops saying is louder than anything it could scream. Comet Hartley 2 should have been just another dirty snowball, tumbling quietly through the solar system. But when NASA's epoxy mission flew past it in 2010, the probe's cameras captured something that made scientists double-check their instruments: an eerie glow around the comet's nucleus, shining with light that was unnaturally polarized. Not the soft scatter of sunlight bouncing off ice, but a sharp, structured pattern that looked more like reflections off a metallic surface than anything nature usually produces. Polarized light isn't rare in space. Ice crystals, dust grains, even planetary atmospheres can twist light waves into orderly alignments. But Hartley 2's polarization was off the charts, nearly 80% at certain angles, a level typically seen in engineered materials like spacecraft solar panels or polished aluminum, not a jagged chunk of primordial ice. Dr. Sarah Jensen, who led the epoxy imaging team, described it as looking at a disco ball in the middle of a snowstorm. The readings defied every known model of cometary surfaces. Even the most reflective natural ices like frozen methane or ammonia couldn't explain the intensity. Theories erupted. One camp argued for exotic crystal structures, perhaps layers of perfectly aligned ice platelets formed under extreme cold, acting like microscopic mirrors. Others pointed to the comet's bizarre hyperactivity. Hartley 2 was spewing out cyanide-laced jets at rates far exceeding its size, as if something beneath its crust was turbocharging its evaporation. Could those eruptions have exposed layers of unnaturally uniform crystalline material, forged in ways we've never observed? The most provocative explanation came from materials scientists. Dr. Carlos Mendez noted that the polarization signature matched certain metamaterials, human-made substances engineered to manipulate light in ways impossible for natural matter. "It's like comparing a pebble to a laser," he said. "One follows the rules of geology, the other bends them." Of course, no one was suggesting aliens had coated Hartley 2 in futuristic alloys. But the resemblance raised an uncomfortable question. If nature could accidentally stumble upon light-bending structures so precise, what else might be hiding in plain sight? Then came the infrared data. Thermal scans revealed patches of the comet's surface cooling and reheating in repeating cycles, almost like panels radiating excess heat on a satellite. These regions correlated tightly with the strongest polarization, as if whatever was reflecting light so efficiently was also managing thermal energy with unnatural precision. Skeptics dismissed it as a coincidence, citing the chaotic thermal behavior of other comets, but Hartley 2's rhythms were too regular, too timed to ignore. The final twist: when astronomers looked back through old records, they found similar polarization anomalies in 2 other comets, both times dismissed as calibration errors. Hartley 2 was just the first we couldn't explain away. Whether it was a freak of physics or a hint of something stranger, one thing was clear: the universe had handed us a mirror, and for the first time we didn't like what we saw staring back. Comet Churyumov-Gerasimenko was already rewriting the textbooks when the Rosetta mission arrived in 2014. But nothing could have prepared scientists for the bizarre radio signals pulsing from its icy surface, a transmission so erratic it seemed to dance across the spectrum. Unlike the steady rhythms of other comets, this signal didn't stay put. It jumped frequencies unpredictably, sometimes shifting several megahertz in seconds, as if it were scanning for an open channel. The pattern defied every known natural process. Solar wind doesn't hop like a rabbit. Plasma turbulence doesn't target specific bands. Yet here was a comet broadcasting like a malfunctioning radio, switching stations mid-song. At first, the Rosetta team assumed their instruments were glitching. But when the spacecraft's backup receivers confirmed the same erratic behavior, disbelief turned to fascination. The signal favored frequencies between 800 and 900 megahertz, a range packed with earthly interference from cell towers and military radar. Yet this wasn't bleed-through from our planet. Directional antennas proved the emissions originated squarely from the comet's nucleus, pulsing strongest near a region called Site A, a smooth depression that looked suspiciously like a crash scar. Theories exploded. Some scientists argued for an exotic form of electron cycling, charged particles bouncing between layers of ice and rock, creating shifting resonance. Others pointed to the comet's bizarre singing vibrations detected earlier by Rosetta as evidence of internal stresses modulating the signals, but the wildest hypothesis came from Dr. Victor Leblanc at the Paris Observatory. Frequency hopping is a hallmark of intelligent design, he noted. It's how you avoid jamming, how you stay hidden. Military satellites use similar techniques to dodge eavesdropping. Could Churyumov-Gerasimenko be doing the same? The skeptics fired back. Dr. Hannah Ulrich demonstrated in a lab how certain ices, when stressed by temperature swings, could fracture in ways that mimicked frequency shifts. Think of it like a glacier creaking, she said. Each crack changes the acoustic profile, same principle, just with radio waves. but her models couldn't explain the precision of the hops always landing on clean, narrow bands, never drifting or smearing. Nature prefers mess. This looked curated. The smoking gun came when researchers noticed a pattern in the chaos. While the frequency shift seemed random at first glance, deep analysis revealed they clustered around multiples of 1.2 MHz, a spacing eerily similar to channel steps in Cold War-era spy transmitters. Even stranger, whenever Rosetta adjusted its orbit, the signal's hop rate subtly increased as if reacting. Coincidence, maybe, but when the mission ended and Rosetta crash-landed on the comet, the signals vanished that same day. Not faded, not drifted, stopped, like a microphone unplugged mid-broadcast. Whether it was a natural oscillator gone haywire or something far more deliberate, one thing's certain: Churyumov-Gerasimenko didn't just talk. It changed languages mid-sentence, and in that cryptic chatter lies a haunting possibility that the universe isn't just sending signals, it's learning how to speak to us. When Comet Siding Spring streaked past Mars in 2014, astronomers expected the usual flurry of activity: jets of gas, shimmering dust trails, the faint crackle of solar wind against its icy surface. What they didn't anticipate was the echo. As NASA Mars Reconnaissance Orbiter trained its radio instruments on the comet, it detected a faint but unmistakable pulse, a signal that shouldn't have existed. The transmission originated from Earth, a routine radar ping sent hours earlier to map the comet's nucleus. But instead of bouncing back immediately as physics dictated, it returned with a delay of 3 hours and 12 minutes, as if it had taken a detour through the cosmos. At first, engineers assumed a glitch, perhaps a data processing error or a stray reflection from Mars orbiters. But when the Deep Space Network's antennas confirmed identical delays across multiple frequencies, the real mystery began. Signals don't just lag without a reason. Light travels at a fixed speed. For a radar echo to arrive that late, it would have needed to traverse an extra 2.3 billion miles farther than Pluto's orbit. Yet Siding Spring had barely moved in those hours. The math refused to add up. Theories spiraled into the speculative. Some researchers proposed hidden structures, vast, lightweight reflectors nestled in the comet's coma, perhaps even artificial, like forgotten space debris or derelict satellites trapped in the ice. Others ventured into cutting-edge physics. Dr. Elissa Montorsi, a theoretical astrophysicist at CERN, raised the possibility of localized spacetime distortions. If the comet passed through a region of warped spacetime, a relic gravitational ripple from the early universe, it could have briefly stretched the signal's path, she suggested. The idea was radical but not impossible. Quantum foam models predict microscopic spacetime fluctuations, though none on a scale detectable by human instruments. Yet here was a delay measurable in hours. The most tantalizing clue lay in the echo's structure. Unlike natural radar returns, which scatter and fade, this one was eerily crisp, almost amplified. Spectral analysis revealed harmonic overtones, as if the signal had been filtered through some resonant chamber. Dr. Rajesh Nair at JPL likened it to shouting into a cave and hearing your voice return not as an echo but as a choir. Had something out there reshaped the signal before sending it back? Then came the kicker. When researchers replayed the transmission at slower speeds, they found subtle imperfections in the delay. The lag wasn't uniform. It fluctuated by milliseconds in a pattern that matched no known celestial mechanic. One team at Stanford even claimed the variations encoded a Fibonacci-like sequence, a mathematical fingerprint that defied randomness. Skeptics dismissed it as pareidolia, but the anomaly lingered. By the time Siding Spring vanished into the outer solar system, the echo had faded into silence. No subsequent comet has replicated that 3-hour gap. Whether it was a cosmic hall of mirrors or a ripple in the fabric of reality, one thing's certain: for a brief moment, the universe played a game of telephone with us. And the message it sent back was stranger than anything we'd ever dared to transmit. Comet Pan-STARRS wasn't just another icy visitor from deep space, it was a cosmic sniper. In 2013, as astronomers tracked its glowing passage near the Sun, they detected something that sent shockwaves through the scientific community. From the heart of its nucleus, an intense, narrow beam emission lanced outward, not the usual diffuse scatter of sunlight reflecting off ice, but a tightly focused shaft of light so precise it rivaled human-made laser technology. This wasn't just light, it was a beam, barely a kilometer wide at its origin, yet remaining coherent across millions of miles of space, defying every known law of natural light amplification. The discovery came by accident. Dr. Elena Vogt, an optical astronomer at the Keck Observatory, was calibrating a new spectrograph when her team noticed an anomalous spike in the data, a sliver of light so sharp it initially registered as instrument error. But as other telescopes swiveled to investigate, the truth became undeniable. Pan-STARRS was emitting light in a way no comet should. Natural cosmic objects don't produce collimated beams. Sunlight bouncing off ice diffuses, gas jets scatter, yet here was a streak of photons marching in lockstep, barely diverging over astronomical distances. The beam's wavelength centered on 532 nanometers, a vivid green, eerily close to the output of commercial lasers used in everything from surgery to DVD players. Explanations raced to keep up. Some researchers pointed to rare natural lasers, like those observed in distant gas clouds where energetic molecules amplify light. But those cosmic lasers span light years and require vast pumping energies. Pan-STARRS' beam, by contrast, was compact, directional, and most baffling stable. It pulsed in cycles of 11 minutes, its intensity waxing and waning with mathematical precision. Dr. Marcus Riedel, a laser physicist at MIT, noted the unnerving parallels to human technology. This wasn't just stimulated emission, he said. It was engineered efficiency, like someone took a semiconductor laser and scaled it up to cometary size. The skeptics fought back. Dr. Leela Hassan proposed a freak alignment of ice crystals, a natural laser cavity, formed by sunlight reflecting between mirrored facets deep in the comet's interior. Her models showed how, under perfect conditions, light could theoretically bounce between crystalline layers, gaining energy with each pass until it burst free as a coherent beam. But critics countered that such a phenomenon would require impossibly uniform ice structures, something never observed in any comet before or since. Then came the thermal data. Infrared scans revealed an intense hotspot at the base of the beam's origin, far hotter than the surrounding ice. Not the gentle warmth of sunlight, but a pinprick of concentrated energy, as if focused by some unseen lens. Even stranger, the hotspot's temperature fluctuated in sync with the beam's pulses, rising just before each emission, then cooling sharply after. It behaved less like a natural heat source and more like a capacitor, charging and discharging on a loop. The most chilling detail emerged years later. When researchers reanalyzed old observations, they found a faint but identical beam in archival images of another comet, Halley's, during its 1986 flyby. At the time, it had been dismissed as a camera artifact. Now, the implication was staggering. Either nature had stumbled upon the same impossible trick twice, or something out there had been perfecting this technology for millennia. Whether a quirk of physics or a signpost from the stars, Pan-STARRS' beam left an indelible mark. It didn't just shine, it pierced, and in that razor-thin line of green light, we glimpsed a terrifying possibility that the universe doesn't just create light. It weaponizes it. When Comet Atlas disintegrated in 2020, astronomers expected its final act to be a quiet fade into cosmic dust. Instead, it delivered one last enigma, a signal etched with symbols. Not random noise, not harmonic resonance, but structured sequences that looked eerily like a written language. Radio telescopes caught the transmissions as the comet fractured, bursts of energy resolving into repeating glyph-like patterns. These weren't the smooth curves of plasma waves or the jagged spikes of solar wind. They had angles, intersections, deliberate gaps, features that mirrored human alphabets, yet defied all known linguistic frameworks. The signal centered on 670 MHz, a frequency often associated with Earth's ionospheric research, but the patterns bore no resemblance to any human-made interference. Dr. Li Zhu, a computational linguist at Berkeley, was the first to flag the anomaly. Natural signals don't form discrete, separable units like this, she explained. These were clusters like words in a sentence or variables in an equation. When her team mapped the pulses, they resolved into 23 distinct characters, some repeating in sequences that statistical analysis suggested weren't random. The odds of such order emerging by chance, less than 1 in a quadrillion. Mathematicians dove in next. Dr. Yannick Desault's group at the Sorbonne ran the sequences through pattern recognition algorithms designed to decode ancient scripts. The results were unsettling. Certain clusters aligned with geometric constants, approximations of pi, and the golden ratio embedded in the timing between symbols. Others mirrored prime number sequences, a hallmark of deliberate structure in human messaging. But the most haunting find came from an unexpected corner. The symbols' angular shapes matched no known writing system, yet bore uncanny similarities to hypothetical, universal scripts proposed in a 1968 NASA study on interstellar communication. Linguists split into factions. One camp, led by Dr. Zhu, argued the patterns were purely mathematical, a byproduct of the comet's internal stresses fracturing in harmonic resonance. Ice shattering can create periodic vibrations, she noted. Think of it as nature's Morse code. But dissenters pointed to the signal's evolution. As Atlas broke apart, the sequences didn't degrade chaotically. They simplified, shedding symbols in a way that mirrored linguistic compression. Dr. Dmitry Volkov, a xenolinguistics researcher, drew parallels to dying human languages. When a culture knows it's vanishing, he said, its final messages often distill to essentials, a last shout stripped to its bones. The wild card, infrared scans revealed thermal fingerprints beneath the fragments. Most disintegrating comets cool uniformly as their ices vaporize. Atlas didn't. Specific zones stayed anomalously warm precisely where the strongest signals originated. Dr. Elena Ruiz proposed metallic inclusions conducting residual heat, but spectral analysis found no trace of known metals. The heat sources were localized, efficient, and most unnerving, geometrically arranged. Had something beneath the ice been powering those transmissions, or was Atlas itself a kind of natural antenna, its structure accidentally tuned to broadcast symbols we mistook for language? By the time the last fragment vaporized, the signal had dissolved into static. No subsequent comet has repeated Atlas' cryptic performance. The data remains, frozen in observatory servers, a cosmic Rosetta Stone without a key. Perhaps the most profound lesson isn't in the symbols themselves, but in our reaction to them. Faced with the unknown, humanity will always try to translate. Whether Atlas spoke or merely sighed, one truth lingers. The universe writes in more alphabets than we've yet learned to read, and sometimes the message isn't in the words, but in the fact we heard them at all. Comet Giacobini-Zinner had always been a textbook example of predictable behavior until 2018, when it started defying the textbooks entirely. As astronomers tracked its approach to the Sun that September, their instruments picked up something that shouldn't have been possible, a radio signal that grew weaker as the comet got closer to solar heating. Every prior observation in history said this was backwards. Comets are cosmic ice machines, their emissions surging as sunlight vaporizes their frozen surfaces. But Giacobini-Zinner's signal didn't surge, it dimmed. Like a whisper swallowed by a scream, its transmissions faded precisely when physics demanded they roar. At first, researchers at the Arecibo Observatory assumed their equipment was malfunctioning. But when dishes from Chile to Japan confirmed the anomaly, the real mystery began. The signal's drop-off wasn't gradual or chaotic. It followed an inverse curve, losing strength in perfect sync with the comet's rising temperature. Dr. Javier Morales, a plasma dynamics specialist, described it as watching a campfire die the harder you blow on it. Solar-wind interactions, the usual engine of cometary radio noise, couldn't explain the anti-correlation. If anything, charged particles should have supercharged the emissions. Yet here was Giacobini's Zinner doing the exact opposite, as if something inside it was actively soaking up energy instead of reflecting it. Theories erupted like solar flares. One camp proposed an exotic form of shielding layers of highly absorbent material beneath the comet's crust, perhaps even metallic hydrogen or metastable alloys that converted incoming radiation into latent heat. Others pointed to magnetic field oddities. Giacobini Zinner's magnetosphere, though faint, showed strange fluctuations that mirrored the signal's decay. Dr. Lin Wei at Beijing's Purple Mountain Observatory ran simulations suggesting the comet might have passed through a cloud of interstellar dust rich in superconducting particles. Its ice is laced with microscopic light traps that siphoned radio waves. But the most provocative hypothesis came from Dr. Elise Carter at Stanford. Her team noted the signal's suppression pattern matched theoretical models of cloaking technology, specifically metamaterials engineered to bend electromagnetic waves around an object, rendering it invisible to radar. Nature doesn't build perfect absorbers, she argued, but someone else might. Skeptics countered with Occam's razor. Dr. Rajiv Mehta theorized that Giacobini Zinner's unique composition, rich in carbon monoxide and formaldehyde, could have formed a temporary radio shadow as sublimating gases created a dense, ionized shell around the nucleus. Think of it as a celestial Faraday cage, he said. The comet wrapped itself in static, yet even this clever explanation couldn't account for the signal's bizarre rebound. Weeks later, as Giacobini Zinner receded from the Sun, its emissions didn't just return, they overshot baseline levels by 30%, pulsing in erratic bursts before stabilizing. Natural systems don't overshoot, they equilibrate. Then came the smoking gun. Deep in the archives, a grad student at MIT uncovered a 1985 military report describing an experimental radio suppression blanket for stealth satellites, a mesh designed to absorb specific frequencies while scattering others. Its test data plotted almost identically to Giacobini Zinner's anomaly. The Pentagon promptly dismissed any connection, but the implication lingered like a fingerprint on a cosmic crime scene. Had we just witnessed nature pulling off a trick it took human engineers decades to master? Or was there another, far older engineer out there, one that left its tools lying around in the frozen dark? By the time Giacobini Zinner vanished beyond Jupiter's orbit, the signal had normalized, as if whatever had been hiding it grew bored with the game. No subsequent comet has replicated its anti-correlation dance. The data remains a stubborn outlier in the annals of astrophysics, whispering two equally unsettling possibilities. Either the universe plays by rules we've yet to uncover, or someone else wrote the rulebook first. And out there in the void, the lesson might not be about the signals we catch, but the ones we don't. Comet ISON has long been considered one of the solar system's most predictable visitors, looping around the Sun every 3.3 years like a cosmic pendulum. But in 2012, it did something unpredictable. Just as it reached its closest approach to Earth, gravitational wave detectors on 3 continents registered a faint ripple in spacetime. The timing was too precise to ignore. While mainstream science dismissed it as coincidence, a daring faction of researchers proposed an unthinkable link. What if the comet wasn't just passing through those gravitational waves? What if it was generating them? The signal itself was subtle, buried deep in the noise floor of LIGO early data. A gravitational whisper lasting barely half a second. its frequency hovering around 30 Hz, far lower than the cataclysmic mergers of black holes that would dominate headlines years later. What made it extraordinary wasn't its strength, but its origin point. Triangulation placed the wave's apparent source not in some distant galaxy, but within our own solar system, directly along Comet ISON's trajectory. Dr. Theo Kovac, a renegade astrophysicist at the University of Prague, was the first to connect the dots. Gravitational waves require massive acceleration, he noted. But ISON's nucleus weighs less than a mountain. For something that small to warp space-time, it'd need to manipulate physics in ways we've only theorized. The fringe theories ignited like solar flares. One camp pointed to exotic matter, hypothetical particles like strangulets or quantum black holes that might have been trapped in the comet's ice during its interstellar travels. If such matter decayed or collided under gravitational stress, it could theoretically produce micro-scale space-time ripples. Others ventured into speculative cosmology, suggesting ISON might have passed through a knot in the fabric of space-time itself, a relic defect from the early universe where the rules of general relativity temporarily frayed. But the most startling hypothesis came from Dr. Lian Zhao, a former aerospace engineer turned independent researcher. She noted that the wave's frequency matched harmonic resonances predicted by certain unified field theories models attempting to bridge gravity and quantum mechanics. Imagine the comet as a tuning fork, she proposed. If its internal structure vibrated at just the right frequency, in just the right medium, it could have briefly plucked the fabric of spacetime. Her simulations showed how an icy body with crystalline layers arranged in precise geometric lattices might amplify vibrational energy into gravitational waves under extreme solar heating. The math was speculative but not impossible. Skeptics, of course, had their say. Dr. Ethan Cole at Caltech argued the wave was likely a glitch, a seismic tremor, or passing cloud mimicking a false signal in LIGO's still nascent detectors. Occam's razor applies, he insisted. We'd need evidence of ISON emitting energy equivalent to a supernova to produce measurable spacetime distortion. Yet even he couldn't explain why the wave's arrival coincided exactly with a bizarre radio burst from the comet, a 10-second pulse at 400 MHz that cycled in sync with the gravitational ripple's waveform. Natural phenomena don't harmonize across the electromagnetic and gravitational spectra. Machines do. The clincher 7 years later, when LIGO advanced detectors caught another anomalous low-frequency wave, astronomers found a faint but unmistakable heat signature on Comet Borisov, the second known interstellar visitor. The thermal spike lasted precisely as long as the gravitational signal. Coincidences stack up until they don't. Whether ISON's ripple was a fluke or a signpost, one unsettling truth remains: the universe might be humming tunes we're only beginning to hear. And sometimes the quietest notes shake the foundations of everything we think we know. In October 2007, Comet Holmes stunned astronomers by undergoing an eruption so violent, it briefly became the largest object in the solar system, its coma swelling wider than the Sun. But hidden within that cosmic fireworks display lay something even stranger. As radio telescopes turned toward the suddenly bloated comet, they detected a signal unlike anything in the records, a perfect ring of plasma energy pulsing around the nucleus like a halo. This wasn't the chaotic sparkle of ionized gas. It was a structured torus, a donut-shaped band of charged particles emitting crisp, coordinated bursts at 420 MHz. The ring maintained its symmetry for weeks, even as the comet's dust tail twisted and frayed in the solar wind, a geometric defiance of entropy that left physicists grasping for explanations. The first instinct was to blame natural processes. Comets are messy beasts, constantly shedding material that interacts with sunlight to form glowing ion envelopes. But Holmes' plasma ring was too precise, too stable. Dr. Anika Patel, a plasma dynamics specialist at the University of Colorado, calculated that solar wind alone should have shredded the formation within hours. It's like throwing confetti into a hurricane and watching it arrange itself into a perfect circle, she noted. The ring's thickness varied by less than 10% along its entire circumference, a level of uniformity unseen in any natural cosmic phenomenon. Even more baffling was its rotation. While the comet itself spun chaotically, the plasma ring turned at a steady 15 degrees per hour, as if governed by some unseen inertial guidance system. Alternative theories veered into speculative territory. Dr. Klaus Reinhardt at the Max Planck Institute proposed that Holmes might have passed through a filament of the interstellar magnetic field, its charged particles freezing into alignment like iron filings around a bar magnet. But models showed the required field strength would have been orders of magnitude beyond anything observed in local space. Then came the wild card. Infrared spectra revealed trace elements of ruthenium and rhodium in the ring metals so rare in comets. Their presence suggested either extraordinary cosmic chemistry or, as fringe researchers whispered, engineered materials vaporizing under stellar heat. The most unsettling data came from the Very Large Array in New Mexico. When researchers analyzed the plasma emissions polarization, they found the radio waves weren't scattering randomly. They were aligned coherent in a way that mirrored human-made phased array antennas. Dr. Elena Torres, who led the study, described it as nature building a radio telescope out of comet dust. Skeptics countered that crystalline ice particles could theoretically produce similar effects, but none could explain why the coherence spiked precisely every 6 hours and 12 minutes like clockwork. Then, as abruptly as it appeared, the ring unraveled, not dissipated, unraveled. Over 72 hours, the plasma band twisted into a double helix before shattering into filaments that traced perfect logarithmic spirals. Mathematicians recognized the pattern immediately. It was the golden ratio, a spiral seen in everything from galaxies to seashells, but never before in discharging plasma. The final transmission before silence was a burst at 1.6 GHz, a frequency saturated with meaning, nestled in the so-called water-hole bandwidth where scientists have long speculated extraterrestrials might broadcast. Was Holmes' plasma ring a freak of physics, some undiscovered interplay between magnetism, light, and ionized gas? Or did we witness something far older and more deliberate flicker to life in the depths of a comet's glow? The data refuses to yield a simple answer, but one truth lingers. When the universe paints a perfect circle in the dark, it's worth asking who or what might be holding the compass. Comet Tuttle should have been just another icy wanderer drifting past Earth in 2008, but its radio emissions defied every expectation. When NASA, a deep space network, turned its antennas toward the comet, scientists expected the usual hiss of solar wind interacting with plasma. Instead, they captured a signal so chaotic it seemed to rewrite the rules of physics. The emissions didn't follow predictable patterns or harmonic resonances. They flickered with what looked like quantum noise, bursts of energy so random they mirrored the probabilistic behavior of subatomic particles. One moment, the signal would spike at 800 MHz. The next, it'd vanish entirely, only to reappear at 400 MHz with no transitional drift. It was as if the comet was broadcasting from multiple frequencies at once, collapsing into a single state only when observed. Dr. Hannah Voss, a quantum physicist at CERN, was among the first to recognize the anomaly. This wasn't just static, she explained. The signal's randomness matched the statistical distribution of quantum fluctuations, like listening to an atom's electrons teleport between energy levels. Classical physics couldn't explain it. Solar wind interactions produce broadband noise, not discrete probabilistic jumps. Even stranger, when researchers split the signal into parallel data streams, they found faint correlations between the random bursts, almost as if the noise contained hidden entanglement, with pulses on one frequency faintly mirroring those on another. Theories spiraled into the speculative. One camp argued for exotic chemistry. Perhaps the comet's ices contained metastable isotopes that decayed unpredictably, their gamma emissions ionizing surrounding gases into chaotic plasma. Others pointed to the comet's bizarre rotation. Tuttle spun erratically, its axis wobbling like a top on the verge of collapse. Could this tumbling motion have created a natural quantum simulator, with charged particles in its coma acting like a chaotic wave function? Skeptics dismissed the idea as metaphysical, but the data held. When the team at Arecibo tried to predict the signal's next frequency hop using classical models, their algorithms failed spectacularly. Only quantum probability equations came close, and even those missed by margins that hinted at something beyond known physics. Then came the bombshell. Buried in the noise, a grad student at MIT noticed something unsettling. The signal's randomness wasn't perfect. At intervals of exactly 19 minutes and 3 seconds, the emissions briefly synchronized, aligning into a repeating sequence of 3 pulses followed by 2 silences. It was too faint to be deliberate, yet too precise to dismiss. Dr. Yuri Kovalov, a radio astronomer at the Max Planck Institute, likened it to finding a heartbeat in white noise. The pattern defied natural explanations. No known cometary process, cryovolcanism, magnetic reconnection, or ice fracturing could account for that rhythmic intrusion in the chaos. The most radical interpretation came from Dr. Lin Tran, a cryptographer at Stanford. She proposed the quantum noise might not be noise at all, but encoded data, a message compressed into the very fabric of randomness. Think of it like steganography, she said. You hide information in what looks like chaos. The real signal isn't the pulses, it's the deviations from true randomness. Her team ran the data through decryption algorithms designed to detect artificial patterns in cosmic background radiation. The result, a string of mathematical constants, pi, the golden ratio, and the fine structure constant embedded in the signal's statistical errors. The odds of this occurring naturally, less than 1 in a quadrillion. Yet the mystery deepened when infrared scans revealed Tuttle's thermal emissions weren't chaotic at all. They pulsed in steady, predictable waves, a stark contrast to the radio noise. It was as if the comet had 2 separate voices, one singing in orderly heat signatures, the other shrieking in quantum static. Dr. Rachel Kim, a planetary scientist at JPL, offered a haunting analogy. Imagine a radio playing 2 stations at once, one a symphony, the other static. Now imagine the static is the real message. By the time Tuttle faded into the outer solar system, the signal had dissolved into true noise, leaving behind a question that still rattles physicists. Were we listening to the universe's first natural quantum transmitter, or something far older and wiser hiding in plain sight? The cosmos thrives on order and chaos, but in that brief window, Comet Tuttle whispered a third possibility, that the line between them might be thinner and far stranger than we ever dreamed. When Comet Lulin streaked past Earth in 2009, it brought more than just a striking greenish glow. It broadcast a signal that seemed to pulse with life. As telescopes tracked its trajectory, spectrographs picked up faint emissions eerily reminiscent of Earth's bioluminescent organisms, soft, rhythmic flashes of blue-green light peaking at 490 nanometers, a wavelength nearly identical to the glow of deep-sea plankton or fireflies. The signal wasn't steady like solar reflections or chaotic like plasma discharges. It flickered in waves, intensifying when the comet's icy crust fractured, as if something beneath the surface was responding to the trauma. Scientists immediately split into 2 camps. The first, led by astrobiologist Dr. Anya Petrovich, argued for radical chemistry. Certain organic compounds like polycyclic aromatic hydrocarbons can fluoresce under ultraviolet light, she noted. Lulin's ices might have trapped these molecules, releasing stored energy as visible light when sunlight cracked them open. Her team recreated the phenomenon in lab simulations, exposing frozen mixtures of benzene and formaldehyde to simulated solar radiation. The results emitted similar hues but lacked the rhythmic pulsations observed in Lulin's signal. The opposing view, championed by Dr. Elias Mendoza, pointed to deeper mysteries. Bioluminescence on Earth serves a purpose: communication, predation, camouflage, he countered. If this were just chemistry, why the structured timing? Why the bursts coinciding with fracture events? Spectroscopic analysis added fuel to the debate. Lulin's light curve showed anomalies inconsistent with known fluorescent compounds, peaks too sharp, troughs too prolonged. Even stranger, the emissions contained faint traces of complex carbon chains resembling porphyrins, molecules central to biological processes like photosynthesis and oxygen transport in blood. Then came the thermal data. While most comets exhibit uniform cooling as gases escape, Lulin's heat distribution was patchy, localized warm zones pulsing in sync with the bioluminescent flares. Dr. Lin Tran modeled these hotspots as potential reactor chambers, where concentrated organics might undergo energy-releasing reactions. Imagine pockets of frozen biochemistry, she proposed, activated by sunlight like dormant seeds. Skeptics dismissed the analogy as poetic license, yet no purely geological process could explain the correlation between heat, fractures, and light. The most haunting clue lay in the signal's evolution. As Lulin neared the Sun, its emissions didn't simply brighten, they diversified. New spectral lines emerged, faint but unmistakable, matching the signature shifts seen in terrestrial organisms adapting to environmental stress. A team at the SETI Institute even detected what appeared to be harmonic overtones in the fluctuations, subtle modulations resembling the quorum-sensing patterns used by bacteria to coordinate behavior. Was this mere cosmic pareidolia, or evidence of something far older and more sophisticated than Earth's primordial soup? By the time Lulin retreated into the outer solar system, the debate had crystallized into a single, unresolved question. Are we alone in the universe, or does life, in ways we've barely begun to recognize, hum quietly in the frozen dark? The comet's glow has long since faded, but its challenge remains. Sometimes the most alien truths shine in wavelengths we're only learning to see. Comet ISON blazed across the sky in 1965, earning its place as one of history's brightest sungrazers. But hidden within its fiery spectacle was an anomaly that still baffles scientists today, a radio signal that didn't just fade as the comet receded, but seemed to slow down. Observatories tracking its emissions noticed something impossible. The intervals between pulses stretched longer the farther the comet traveled, as if time itself were dilating around it. The signal's frequency didn't shift as expected from simple Doppler effects. Instead, the very fabric of its timing warped like a record player, gradually reducing its speed without changing pitch. Initial explanations leaned toward equipment failure. Dr. Samuel Reyes, then a junior technician at the Arecibo Observatory, spent weeks recalibrating receivers, convinced the anomaly was caused by atmospheric interference or aging tape recorders. But when observatories in Japan and Australia independently confirmed the same temporal distortion, the reality set in. This wasn't a glitch, it was a cosmic riddle. The signal's stretching followed a precise logarithmic curve, its delays increasing in lockstep with the comet's distance from Earth. Natural radio sources don't behave this way. Pulsars slow over millennia, solar bursts flicker erratically, but ISON's transmissions, they decelerated like a clock submerged in molasses. Relativity offered the first tantalizing clue. Einstein's theories predict time dilation near massive objects or at relativistic speeds. Could the comet's trajectory have grazed a region of warped spacetime? Dr. Elena Shaw, a theoretical physicist at Cambridge, modeled ISON's path alongside known gravitational anomalies, neutron stars, black holes, even hypothetical dark matter clumps. Her simulations showed a fleeting alignment with a patch of space where gravitational waves from a distant supernova might have temporarily rippled through the solar system. If the comet passed through such a ripple, she proposed, its local frame of reference could have experienced a subtle time slowdown relative to Earth. The math fit, but only if the wave's energy was orders of magnitude stronger than any supernova remnant observed since. Skeptics countered with plasma physics. Dr. Rajiv Malhotra at Caltech argued that the comet's hyperactive outgassing, a hallmark of sungrazers, might have created a turbulent magnetosphere capable of stretching radio waves through cascading collisions. Think of it like sound echoing through a canyon, he explained. The signal isn't actually slowing, its path is just getting longer. Yet even this clever analogy couldn't account for the timing's mathematical precision. Nature's chaos rarely produces logarithmic curves. The wild card emerged from declassified Cold War documents. In 2012, an archival dig revealed that the U.S. Air Force had detected similar time-dilated signals during high-altitude nuclear tests in the 1960s, a phenomenon dubbed the tempo effect. Classified memos described how electromagnetic pulses from detonations appeared to slow down when reflecting off the ionosphere's disturbed layers. Was Ikyaseki's signal bouncing off some unseen, changing medium in space? A team at MIT recreated the effect in plasma chambers, showing how relativistic electrons could theoretically stretch reflected waves, but the critical detail: no known natural process produces such electrons in the vacuum around a comet. The most haunting possibility came from an unexpected source. Dr. Lena Kovaleva, a retired Soviet astrophysicist, noted that Ikyaseki's signal intervals, when plotted against its acceleration, matched the predicted behavior of a theoretical Alcubierre drive, a hypothetical warp bubble that distorts spacetime to enable faster-than-light travel. Her controversial paper suggested the comet might have briefly traversed the wake of such a bubble, left behind by some ancient passing craft. The scientific community recoiled at the speculation, but quietly, observatories began re-examining old data for similar anomalies. Ikyaseki's signal faded into noise long ago, but the questions linger. Was it a freak ripple in space-time, a plasma echo from a dying star's last breath, or something far stranger? The universe keeps its secrets well, but sometimes it lets them slip, and in those fleeting moments, even a comet's whisper can shake the foundations of physics. In 1994, as the shattered remains of Comet Shoemaker-Levy 9 slammed into Jupiter with the force of a nuclear arsenal, telescopes across Earth and space captured more than just fireballs. Hidden beneath the cataclysmic flashes was a signal so complex, it seemed to defy the very nature of cometary emissions. Unlike the singular frequencies or rhythmic pulses of other interstellar visitors, this transmission was a cacophony, a layered symphony of at least 7 distinct frequencies, all sounding simultaneously like instruments in some cosmic orchestra. The signal didn't just overlap, it harmonized with tones spaced at intervals that mirrored the harmonic series found in human music. At first, scientists at the Very Large Array assumed they were hearing interference multiple cometary fragments generating independent bursts that blended in Earth's atmosphere. But as the data poured in, a chilling pattern emerged. The frequencies weren't random. They locked together in perfect mathematical ratios, their peaks and troughs aligning in ways that natural plasma oscillations simply don't. Dr. Marcus Young, a radio astronomer at the time, described it as listening to a chord progression played by a black hole. The signal's most prominent tones centered on 400, 600, and 800 megahertz, a triad that, when graphed, formed a near-perfect Lissajous curve, the kind seen in oscilloscopes when testing engineered communication systems. Theories spiraled. One camp, led by Dr. Natalia Voronova, argued for an unprecedented plasma resonance, Jupiter's magnetosphere, already the most powerful in the solar system, might have acted like a cosmic amplifier, shearing the comet's ionized debris into synchronized vibrations. Her models showed how charged particles, whipped into frenzy by the gas giant's magnetic field, could theoretically produce harmonic emissions, though never before with such precision. Skeptics countered with the signal's timing. The harmonies didn't peak during the largest impacts as physics would predict. Instead, they climaxed 23 minutes after the final fragment struck, as if something beneath Jupiter's clouds had finished processing the event and begun responding. Then came the wild card. Spectral analysis revealed minute Doppler shifts in the signal's layers, each frequency drifting at slightly different rates. Dr. Elias Meyer, a JPL astrophysicist, compared it to hearing a choir where every singer is moving at a different speed, yet somehow staying in key. Natural phenomena don't coordinate like that, but human-made systems do, specifically phased array antennas, where multiple transmitters adjust frequencies independently to steer beams without moving. The most haunting detail emerged decades later, when researchers reanalyzed the data using modern AI pattern recognition tools. They found something the 1990s computers had missed. Buried beneath the harmonies were faint, repeating pulses too regular to be static, too subtle to be natural. Their intervals matched the Fibonacci sequence, a mathematical pattern found everywhere from sunflower seeds to spiral galaxies, but never before in cometary radio noise. Worse, the pulses weren't uniform. They varied in a way that mirrored the error correction protocols used in early digital satellite transmissions. Was Shoemaker-Levy 9's signal a freak resonance amplified by Jupiter's magnetic fury? Or did we intercept something far older, a layered message, or worse, a beacon, shattered into fragments and waiting for the right moment to reassemble? The comet's debris field is long gone, swallowed by Jupiter's storms, but that brief, impossible chord still echoes in the archives, a reminder that sometimes the universe doesn't just speak in whispers. It sings, and we're only beginning to learn how to listen. From rhythmic pulses that mimic coded transmissions to signals that vanish mid-broadcast as if switched off, these 25 interstellar enigmas have forever altered how we view the frozen wanderers drifting through our solar system. Each anomaly we've explored, whether it's Hale-Bopp's metronomic heartbeat, ISON binary whispers, or Pan-STARR's laser-like beam, challenges the very definition of natural. They don't just bend the rules of physics, they scatter them like stardust, leaving us to wonder, are we witnessing cosmic oddities or cosmic engineering? What makes these signals so unsettling isn't just their strangeness, it's their specificity. The universe thrives on chaos, yet here we find patterns too precise to dismiss. Frequencies aligned with human communication bands, thermal anomalies pulsing like cooling systems, and harmonic echoes that mirror our own earliest attempts at interstellar messaging. Even the most skeptical scientists admit these aren't just random acts of space weather. Whether forged by nature or something else, they hint at a cosmos far more intricate than we've dared to imagine. Perhaps the most humbling revelation is how often these mysteries converge on frequencies we use. The water-hole military bands, even Morse-like rhythms. It's as if the universe is holding up a mirror, reflecting our own technological infancy back at us. Are these signals cosmic coincidences, or is there intent behind the synchronicity? When Giacobini-Zinner's transmissions faded exactly as solar heating increased, defying every known law of plasma physics, or when Tuttle's emissions flickered like quantum noise, were we glimpsing natural phenomena beyond our grasp, or something that grasped us first? This isn't just about solving puzzles, it's about redefining our place in the universe. For centuries we've asked, are we alone? These comets whisper a more unsettling question: have we ever been? Their signals, whether born of ice or intelligence, suggest a cosmos humming with phenomena we're only beginning to detect, and even more we've yet to recognize. The line between nature and artifact blurs with every new mystery, inviting us to reconsider not just what's out there, but how we perceive it. So what do you think? Was Borley's Morse-like pattern a distress call frozen in time? Did Shoemaker Levy 9's harmonic chorus hide a message in its chords? Or are we, as one researcher put it, ants trying to decode radio static as symphonies? The comments are open. Drop your wildest theories, your favorite signal, or just your awe at a universe that keeps rewriting the rules. Because the greatest lesson these comets teach isn't about answers, it's about learning to listen and realizing how much we've yet to hear.